since this was so much fun, let's solve more problems involving second-order ODEs. And in particular, let's solve the ODE whose auxiliary equation is the following monster. So r to the fourth times r minus 1 squared times r squared plus 1 times r squared plus 4r plus 5 squared equals 0. Now, of course, it's not a second-order ODE here, but we can still solve it using our techniques. So I think it becomes 4 plus 2, 6, 8, and then plus 4. It's a 12th order ODE. Oh my God. All right. So in this case, let's find the roots. It's not too bad. So we have r equals 0, which is a quadruple root. And then we have r equals 1, double root. And then r squared plus 1 equals 0. That's r is plus minus I. And then the other one, by completing the square, you can check that we have r equals minus 2 plus minus I, which is also a double root here. So double complex root. And let's see what we can do with this information. So r equals 0 would give us a e to the 0t, which is just a. Now, since 0 is repeated twice, we put an extra t. So bt e to the 0t. Since it's repeated 3 times, we put ct squared e to the 0t. And since now it's a quadruple root, it's dt cubed e to the 0t. All right, that takes care of the 0 root. And then r equals 1 double root gives you e to the t plus ft e to the t. The complex root plus minus I gives us cosines and sines. So g cosine of t plus h sine of t. And finally, I think the most interesting one, so this minus 2 plus minus I, well, as usual, it would give you I e to the minus 2t cosine t plus j e to the minus 2t sine of t. That's if it were not repeated. But since it's repeated, so because of the square term here, we have to add an extra t. So that would give you, I think, I forgot my alphabet, so kt e to the minus 2t cosine t plus lt. Some people might say it's lit. I say it's lt e to the minus 2t sine of t. So the whole point is, if you can solve the auxiliary equation, so if you can find roots to the auxiliary equations, you can technically find any solutions to a constant coefficient higher order ODEs. That was one example. Another one I wanted to mention, this is very cute. So let's try to solve y double prime minus 4y prime minus 21y equals 0, but with the additional assumption, so such that as t goes to infinity, your solution goes to 0. Now, it's a kind of non-standard condition, but important thing in application. Like we have, let's say, oscillations, and we want to figure out when do the oscillations go to 0. But same thing as usual. So we find the auxiliary equation, r squared minus 4r minus 21 equals 0. You can factor this. So you want the product to be minus 21. So I think r plus 7 times, or no, not r plus 7, r plus 3 times r minus 7 times r minus 7 equals 0. Because again, product is minus 21, the sum is minus 4, and that gives you r equals minus 3, and r equals 7. And therefore, the general solution would be a e to the minus 3t plus b e to the 7. And now, well, we cannot really find initial conditions, but we can figure out what happens as t goes to infinity. Notice this whole term as t goes to infinity goes to 0, no matter what a is. But this e to the 7 term, it blows up to infinity, right? So the problem is this whole term might go to either infinity or minus infinity, unless in the special case where b is 0. And so in particular, if b is non-zero, this term goes to plus or minus infinity. So whole solution goes to plus minus infinity. So if we want it to go to 0, we need to have b equals 0. So if we want y of t goes to 0, we need b equals 0. So in fact, b equals 0, and therefore y of t is a e to the minus 3t, which indeed goes to 0 as t goes to infinity, which indeed goes to 0 as t goes to infinity. And that's all. We found kind of all the solutions that go to 0 as t goes to infinity. I mean, how cute was that? Don't you love that problem?